Hello, I'm John Doherty. Welcome to another short video on the nuts and bolts of using a particular aspect of PEST or PEST++. This video looks at covariance matrices, how to build a covariance matrix file and how they're used. So what programs read a covariance matrix file? Well, PEST reads a covariance matrix file if asked to do so. Suppose we've just added regularisation to a PEST control file, using, for example, the addreg1 or addreg2 utilities. These programs add prior information equations to the bottom of a PEST control file, and in doing so they all ascribe to all of those equations a weight of 1. Each of these prior information equations endows a parameter or suggests to PEST that that parameter's value should be equal to its initial value as recorded in the parameter data section of the PEST control file. When we do this for parameters like pilot points, it's much better to use a covariance matrix than weights. This assures that any emergent heterogeneity is spread out and not just concentrated at pilot points, producing a bullseye's effect. To do that, we can add the name of a covariance matrix file to the observation groups section of the PEST control file. We write the name of the pertinent covariance matrix file next to the name of the observation group that is assigned to the pertinent prior information equations. Then PEST uses the covariance matrix instead of weights. Covariance matrix files feature prominently in parameter uncertainty files. A parameter uncertainty file has multiple blocks. Here's an example: standard deviation blocks, covariance matrix blocks, and each one of these covariance matrix blocks features the name of a covariance matrix file. So here's the name of one file, another and another, all covariance matrix files. Plus there is some information on how to link the elements of the covariance matrix to parameters that are contained in the parameter data section of the PEST control file. See the parameter uncertainty file video for more details. A parameter uncertainty file normally contains information pertaining to the prior probability distribution of parameters. This is used whenever we want to, for example, generate random realizations of parameters. For example, if we're using PEST PPIES or Monte Carlo analysis. It's also used if we want to do linear uncertainty analysis. So parameter uncertainty files are used by a lot of programs from the PEST and PEST++ suites, and many times they will feature covariance matrix files. Before we discuss the building and storage of a covariance matrix, let's take a few moments to just look at what a covariance matrix is. Suppose we have a random vector x. A random vector is a vector whose elements are all random. These slides, by the way, are taken from another video on the mathematics behind PEST and PEST++. So here we have a random vector x, its elements are random, and let's suppose there are n of these elements. These elements have a mean, but to describe the variability about that mean, we use a covariance matrix. Now if we have n elements of this random vector, the covariance matrix has n times n elements, so it can become rather large. If we have non-zero off-diagonal elements, that indicates statistical interrelatedness between respective elements of this random vector x. The matrix Cx has special properties. It's square, it's symmetric, but more than that, it's positive definite. That means for any non-zero vector x, this relationship is obeyed, and that's a special relationship for a special type of matrix. The diagonal elements of a covariance matrix specify the variances of respective elements of the x vector. Variance is the square of standard deviation. The definition of variance is the expected value of a random variable minus its mean squared. Off-diagonal elements of a covariance matrix specify covariances between pairs of elements of the x vector. The definition of covariance is the expected value of one random variable minus its mean times another random variable minus its mean. So collectively, the covariance matrix specifies the variability, the ability to wiggle of these elements of x about their means. Now, if we have a large random vector of, for example, pilot point parameters, we have to come up with a way of building a large covariance matrix that specifies variability of those parameters and correlation between them. To do that, we make a couple of simplifying assumptions. These assumptions are sort of reasonable and sort of not. We will get more complicated as this video progresses. Here we've got a regionalized random variable. So now we're wandering into the field of geostatistics. This might be, for example, colored according to the value of hydraulic conductivity throughout a model domain. It's random because we don't know exactly what hydraulic conductivity is, but we have a statistical distribution of it, or at least we have a statistical distribution if we're prepared to make some assumptions. Normally we work with pilot points, so we work with samples of this regionalized variable. We have a vector, a random vector, a vector of, say, hydraulic conductivities at each one of these pilot points. So there's our random vector. We need a covariance matrix for that vector. How are we going to build this? Well, we make the first assumption, which is that the covariance between the parameters associated with any two pilot points is a decaying function of distance. That is, if two pilot points are reasonably close together, the covariance between them is higher than for two pilot points that are further apart. That's the first assumption, that the covariance between the parameters associated with the pilot points decays with distance. The second assumption is what we call stationarity. Now we'll make this assumption now and we'll vary it later. We assume that this function that describes the decay of covariance with distance is the same function here as here as here. That is, it applies throughout the model domain. So whenever we want to calculate the covariance between parameters associated with two pilot points, we simply work out how far apart they are, then apply this function to work out the covariance. Suddenly, the task of filling that covariance matrix becomes fairly simple. This function tells us the range at which correlation dies out, and the value at a separation of 0 is the variance, that is the wiggle room, the uncertainty of that parameter. Now, as I said before, we're wandering into the field of geostatistics here, and geostatistics more often describes this same phenomenon using a semi-variogram. Now, we're not going to talk too much about a semi-variogram in this video. All that needs to be said is that this brown curve is the same as this green curve, just turned upside down and moved up. So semi-variogram gives us a completely adequate way to describe decay of covariance with distance. You can use one or the other. The variability, the variance of the hydraulic property simply is it's called the sill if we're talking about a semivariogram, and it's the value of the semivariogram at very large distances. The range remains the same. So what equations can we give to this decaying function of covariance with distance? Well, not just any equation will do. Remember, the covariance matrix that emerges from application of this equation must be positive definite. That restricts us to the use of certain equations. And the equations that are listed here are the most commonly used ones. There are other equations, but these will do the job most of the time. Sometimes it's convenient to add a little bit of randomness just associated with each point. This is called nugget. That means we move this variogram up, we put a little blip here at the h value, a distance value of 0. The nugget is randomness that just exists at each point and shows no spatial correlation. The addition of a nugget is something that's available through most of the utilities that we'll talk about in the rest of this video. Now let's briefly look at how a covariance matrix file is stored. Here's an excerpt from such a file. It's a text file. A large matrix is stored in this file. But according to PEST matrix file protocol, before we have the matrix, we have a header line with 3 integers: number of rows, number of columns, and a little code there which says something about the type of matrix to follow. The number of columns and the number of rows, of course, are equal to the number of parameters to which the covariance matrix pertains. Now, optionally, following the actual matrix, we can have another section of this file with a header called row and column names. Then we may have listed the names of all the parameters to which rows and columns of the covariance matrix file pertain. There has to be as many entries here, of course, as the number here, the number of rows and columns in the covariance matrix, which, as I said before, is the number of parameters to which the covariance matrix pertains. Now, a covariance matrix file which adopts this protocol is built by members of the ppcov utility family, and we'll see them in operation in a moment. Members of this family of utilities optionally formulate parameter names by adding a user-supplied prefix to the names of pilot points, and they get those names from a pilot points file, which we'll see in a moment. So that's option 1. Option 2 dispenses with this second part of the covariance matrix file, or if this second part is present, it's simply ignored. A covariance matrix file of this type can be built by any of the ppcov family, also by plproc, but you can write a program yourself which can build a covariance matrix file which adopts this protocol. That leaves the question, however, of how are rows and columns of the covariance matrix file linked to parameters in a pest control file. Well, there are a couple of options here, and these are described in detail in another video, the video on parameter uncertainty file. Option 1 is to supply another file which just lists parameter names in the same order as row and column names in the covariance matrix file. The linkage to parameter names within a pest control file is therefore easy. Or the first parameter, last parameter protocol in the parameter uncertainty file can be adopted. This is normally easy too. If a covariance matrix file is cited following the name of an observation group in the observation group section of a pest control file, then it is assumed that the ordering of rows and columns in the covariance matrix file is the same as the ordering of prior information equations to which those rows and columns pertain. And that, of course, the number of rows and columns is equal to the number of pertinent prior information equations. This is pretty easy to do actually, just from the way that covariance matrix files are built. They're built from a pest control file. The parameter data section of a pest control file is normally built from a pilot points file. Sorry, I meant to say pilot points file before. A covariance matrix file is normally built from a pilot points file. The parameter data section of a pest control file is normally built from a pilot points file. When regularisation is added to a pest control file, it normally follows the same sequence of parameters as are recorded in the parameter data section of a pest control file, so order is maintained automatically just in the way all these various files and file segments are built. So this is not a problem. The ppcov utilities, which we'll talk about in a moment, read two types of file. The first type of file they read is a structure file. Structure file is easily prepared using a text editor. It's divided into blocks. Two types of blocks, a structure block or a variogram block. A structure is a geostatistical structure, and a geostatistical structure can be comprised of 1 or 2 or 3 or 4 or 5 variograms. Normally we just use one. So in this particular structure file, two structures are cited, struct1 and struct2. Each structure has a name. The name of the structure is written beside the introductory keyword for the block. Now, struct1 has two variograms that comprise the geostatistical structure. Struct2, there is only one variogram which comprises the geostatistical structure. For struct1, these variograms are var1 and var2. So each variogram has a name, and that name is cited here, so we know which variogram is part of which structure. Struct2 has one variogram, and that is var3. The amount of each one of these variograms that comprises the structure is specified following the variogram keyword. So this is the CIL applied to variogram 1, this is the CIL applied to variogram 2, or var1, var2. A CIL of 0.5 is applied to var3 by struct2. Now, structure could use one of these other variograms. A variogram can be reused in multiple structures if desired. The type of variogram, the equation describing the variogram, and hence the decay of covariance with distance, is specified by an integer. 2 for exponential, 3 for spherical, 4 for power, 3 for Gaussian. The A value of the variogram, which features in these equations that we saw early, which describes decay of covariance with distance, is provided through the A keyword. Anisotropy is allowed, so the correlation length can be different in different directions. If that's the case, the bearing of the major axis of anisotropy must be supplied together with the anisotropy ratio itself. This keyword here, transform, which is part of the structure block, is there for our benefit. We'll see this again shortly. This is to remind us that if we're building a covariance matrix for parameters which are log transformed in a pest control file, then the statistics that allow us to build that covariance matrix must apply to the log of parameters and not the native parameters. Here's a 3D structure file. Very similar in that we've got blocks for structures and blocks for variograms, and a structure can hold more than one variogram. The CIL is assigned through the variogram keyword in the structure block. The variogram block is slightly different to accommodate the three-dimensional nature of the variogram. It can easily accommodate anisotropy, and when we're dealing with three-dimensional variograms, there normally will be considerable anisotropy in the vertical direction. The A values, the correlation lengths in the different directions, can be specified together with the directions to which those A values pertain through these ANG keywords. The other type of file which members of the ppcov suite read is a pilot points file. Now, a pilot points file has a fairly rigid structure, but this isn't the only option for building a covariance matrix. We'll talk about another option shortly, which allows much more flexible input of data on which to build the covariance matrix. But for the moment, let's focus on a 2D pilot points file. This file has 5 columns. The first is the name of the pilot point eastings, northings, the zone to which each pilot point belongs, and the parameter value associated with each pilot point. Now, members of the ppcov suite don't actually need this parameter value, but they require the presence of this column. No header is allowed in this file. Entries on each line can be space, tab, or comma delimited. Now let's just say a couple of words about zones. Different pilot points can be assigned to different zones. Zones are denoted by an integer. There is no correlation across zone boundaries. Different geostatistics can apply within different zones. As we'll see in a moment, members of the ppcov suite accommodate the assignment of pilot points to different zones as they build the covariance matrix pertaining to the pilot points as a whole. That covariance matrix will therefore have different blocks. One block will pertain to pilot points in zone 1, the other block, in this case, will pertain to pilot points in zone 2. A 3D pilot points file is very similar. Name, easting, northing, elevation. That's the only extra column required to accommodate the third dimension when we're dealing with 3D pilot points file and construction of a covariance matrix for 3D pilot point parameters. Again, fairly rigid specifications, no column headers. Columns can be space, tab, or comma delimited. Now let's run ppcov. ppcov is a member of the Pest Groundwater Utility Suite. To run this program or any other program from that suite, you type its name at the command line prompt. ppcov begins execution by asking you for the name of the pilot points file that it must read. Now, once it reads the contents of that file, it asks a curious little question. This is a quality assurance measure. It checks that you haven't made any mistakes unintentionally in the pilot points file. It wants to make sure that you haven't unintentionally put one pilot point on top of another or put two pilot points too close together. So it asks you, what's the minimum allowable distance between pilot points in the same zone? I normally answer 0 to this question, but if any two pilot points are on top of each other, ppcov will provide an error message and then cease execution. Again, this is a quality assurance measure. Putting two pilot points on top of each other, by the way, happens more often than you'd think, so it's a good quality assurance measure. ppcov then asks for the name of the structure file which it must read. Then, for every zone that it discovers in the pilot points file, it asks you to associate a geostatistical structure read from the structure file with that zone. So let's associate struct1 with zone 1 and struct2 with zone2. ppcov then asks for the name of the covariance matrix file that it must write, and then it asks if you want to adopt the naming protocol where you link elements of the covariance matrix to parameter names through a prefix added to pilot point names. I normally don't do this, but if you want to, you can. I normally just hit enter in response to this prompt and link rows and columns of the covariance matrix to parameters in a pest control file using one of the other methodologies that we talked about earlier. So ppcov then writes the covariance matrix file, and then in this case issues a little warning. And that warning comes back to the transform keyword. Now that transform keyword, remember I said it was for your benefit only. ppcov just warns you that if you're going to use the covariance matrix that it has just written, this must apply to the log of any parameters that are log transformed. And it just makes sure that you're aware of the fact that the statistics that were used to build that covariance matrix file pertain to the log of parameters if in fact this covariance matrix is going to be used with parameters that are log transformed in a pest control file. Using ppcov isn't the only way to build a covariance matrix. You can also use plproc. Now plproc is discussed in other videos. plproc is normally used as a model preprocessor, as that model is being history matched, undertaking uncertainty analysis under the control of pest or pest++. But plproc can do other things as well. Included amongst them is generation of a covariance matrix. Other plproc functionality is listed on this slide. It's mainly tuned to using pilot points to constructing interpolation factors between pilot points and a model grid and implementing various other types of interpolation schemes. It can work in 2 and 3 dimensions. It can write input files for complex structured or unstructured gridded models. But one of the things and it can handle things like structural overlay parameters which have got nothing to do with pilot points. The focus of our interest here is generation of a covariance matrix. So let's have a quick look at how we can use plproc to build a covariance matrix. plproc, as I just said, can do quite complex operations as it manipulates parameters to build input files for structured and unstructured gridded models. It can do a sequence of operations, and each one of those sequence of operations is invoked through a function call. Here we have a simple plproc script which has 3 function calls, and the second one of these functions is a call to build covmat from vario, that's the name of the function, and this function can build a covariance matrix. The first function simply reads data about pilot points. Now the file from which plproc can read pilot point related data is a lot more flexible than a pilot points file that ppcov reads. plproc will read a pilot points file that ppcov reads, no problem, but it'll also read pilot point data from other types of file as well, with extra columns present or not in that file, with headings present or not in that file. Then, using function build covmat from vario, plproc builds a covariance matrix. As we'll see in a moment, this function can actually be quite complicated. It can build 2 and 3 dimensional, well, it can build 2-dimensional matrices for 3-dimensional sets of pilot points. It can accommodate anisotropy. It can accommodate spatially varying variograms. Once the covariance matrix is built, that covariance matrix is recorded on a file. Note that this file does not have that columns and rows header followed by parameter name, so you have to link the rows and columns of the covariance matrix to parameters in a pest control file using one of the other options that I mentioned previously. To run plproc, you type its name at the command line prompt, followed by the name of the file that contains the script that it will run once it is invoked. plproc generally runs quite quickly, executing each one of its commands or calling each one of those functions and doing it what the functions tell it to do. In this case, it finishes operations by writing the covariance matrix file that we wrote the script asking for it to write. So how appropriate is the assumption of geostatistical stationarity? Well, there's going to be a lot of cases where it's not really appropriate. Groundwater model domains can cover large areas, and stationarity might not be a good assumption at all. So here's a model domain in which we've placed an unstructured grid, and perhaps the outcomes of site characterization suggested in one part of the model domain. We've got spatial correlation lengths shown by this ellipse, this distance in this direction and this distance in the orthogonal direction. Perhaps things are the same here, but not here. Perhaps in this case the direction of an isotropy has shifted, and indeed also the correlation lengths in different directions may be different. Perhaps in this area here we've got some structure necessitating large spatial correlation in one direction and small correlation in an orthogonal direction. And then perhaps in other parts of the model domain we're back to isotropic conditions or mildly anisotropic conditions. We could have a pilot point at the center of each of these ellipses, but more likely we'll have lots of pilot points. But what we can do is we can accommodate the fact that at each one of these pilot points, the characteristics of the variogram, which describe just spatial correlation and anisotropy possibly at that point, they may be different from other points. This may be smoothly varying function of space, these geostatistical characteristics, all of them, or it might be that there's similarity in some places, similarity in others with a boundary between them. It doesn't matter. The point is that we can, if we like, have different geostatistics ascribed to all of the different pilot points that we use to parameterize our model. And this is done through a file called a pilot point statistical specification file. The file has the columns that you can see here. The header to those columns is optional. So we've got the pilot point name, X and Y coordinates, zone number if appropriate, nugget, SIL, A, the anisotropy ratio and bearing. On each line of that statistical specification file, entries are separated by space, tab or comma. The program which uses this file is called ppcov SVA. SVA stands for spatially varying anisotropy. This is another member of the PEST groundwater utility suite. To run ppcov SVA, we type its name at the screen prompt, and it immediately asks us for a statistical specification file. We provide the name. Then if there's no header at the top of the file, we answer yes. No, we don't skip a line at the top of the file. If there is a header, we skip a line at the top of the file. We're then asked that same quality assurance question that we were asked before, just to make sure that no two pilot points are on top of each other. Now, even though the specifications for the variogram can vary from pilot point to pilot point, the variogram type has to be the same throughout the model domain. In this case, we specify exponential variogram. ppcov SVA then asks for the name of the file that it must write. It constructs the variogram and writes the file, but first it asks, should it link entries of that covariance matrix, rows and columns of the covariance matrix, to parameters in a pest control file by adding a prefix to pilot point names. If you don't want to do this, just hit enter. And then it goes ahead and writes the file. This file will include the covariance matrix. If you just hit enter here, these will be pilot point names without any prefix. It's optional whether you use this section of the file or not when linking the covariance matrix to parameters in a pest control file. Alternatively, rather than using ppcov SVA, you can use plproc to do the same thing. plproc, as we said before, is quite flexible in how it can read its data. It can read a pilot point statistical specification file, or it can read another file that's similar that contains less columns or more columns. The header is optional. plproc can accommodate a lot of flexibility in the files from which it reads pilot point data. We then use this same function that we used before, build covmat from vario, but in this case the arguments are different, and the arguments are such as to allow us to specify, to associate different variogram properties with different pilot points. So it then constructs the covariance matrix in the same way that ppcov SVA constructs the covariance matrix. Once that covariance matrix is built, it is then written to a file using the last of these functions. In this case, the protocol adopted is such that the covariance matrix is stored, but there's no parameter names following the covariance matrix. To run plproc, we type its name followed by the name of the file containing the script that we want plproc to run. So in this case, plproc.dat. plproc runs and writes the file. So this is the other option by which we can construct a covariance matrix file embodying a covariance matrix that is built according to spatial correlation statistics that vary in space throughout a model domain. Now, use of spatially varying geostatistics can be quite useful for reasons other than accommodating spatially varying hydrogeology. Often this can be a good way to accommodate spatially varying information density. Suppose I've got a model domain and that these are my observation wells, and that I've got heads in these observation wells, and these comprise my calibration data set. Now, I may emplace pilot points throughout that model domain with a spatial density which reflects the spatial density of the observation wells. I have more pilot points where there's more information that I want to capture. Less pilot points where there's less information. And I do that because I'm kind of anticipating that the more information I've got through these heads, the more likely it is that bits and pieces of heterogeneity will arise, will emerge through the calibration process informed by the heads in those wells. In parts of the model domain where observation wells are further apart, the calibrated parameter field will express more spread out heterogeneity, not because there's any less heterogeneity in this part of the model domain under the ground. It's just that my ability to capture that heterogeneity is limited because there's less data in that area. So in response to this situation, I may say then that when I'm building a covariance matrix for these pilot points, particularly for regularisation purposes, that I expect a greater length of spatial correlation here than here, simply because the distance between pilot points is greater here than here. And the distance between pilot points is greater here than here because there's less information to capture, less heterogeneity that I may need to express. Now, as we said before, we don't want bullseyes, we don't want point-by-point response to information contained in a calibration data set. We want any heterogeneity that emerges from calibration to be spread over a few pilot points rather than just point by point. So I have to have a covariance matrix. But the range of the variogram on which that covariance matrix is built should be a lot less here than it is here, simply because pilot points are closer together here than here. Now I can accomplish this using a utility named makeppstat. This is one of the groundwater utility suite programs supplied with PEST. So let me run mkppstat now. I type its name at the command prompt. It asks for a pilot points file. It then reads that pilot points file. And for every pilot point in that file, it works out where that point is in relation to other pilot points. It then asks me, how many neighbours of that pilot point do you want me to use when calculating how far pilot points are apart in that part of the model domain? In this case, I say 4. So for each pilot point, it looks at the closest 4 pilot points and calculates the average distance between the pilot point that I'm interested in and its closest 4 neighbours. Then it says multiply that average distance by what factor to calculate a local variogram range, or the A value that's used in calculating the covariance versus distance function. I supply 1.5 in this case, then makeppstat builds me a pilot point statistical specification file. Now this file may need modification if I want to introduce anisotropy, but often it won't. This file can be used by ppcov SVA, it can be used by plproc to build a covariance matrix based on variograms that reflect local pilot point density that in turn reflect local density of information used in the history matching process. Finally, I want to say a few words about working in 3 dimensions. Everything we've talked about so far can be applied in 3 dimensions as well as in 2 dimensions. The pilot point statistical specification file for 3 dimensions is similar to that in 2 dimensions. The header line is optional. Entries within a row, a space tab or comma delimited. There's a few more columns just to take into account the extra direction. The correlation lengths in 2 horizontal directions and the vertical direction, and the angles to which these A values pertain. Using the makeppstat 3D utility, you can build a 3D pilot point statistical specification file that can be used by ppcov 3D, SVA or plproc to build a covariance matrix file. But just be careful. When we're working in a real-world situation, correlation lengths in the vertical direction are often a lot less than in the horizontal direction. And that has to be reflected in the covariance matrix file that we build. However, this can be difficult. Normally, correlation is not planar but tends to follow the surface of the Earth or layering within a model domain. It's very easy when we're dealing with a high degree of vertical anisotropy to get that correlation wrong. For example, take these 2 points. The line joining these 2 points follows the surface of the Earth. They're in the same layer. We expect high correlation, but if you specify a high degree of vertical anisotropy with low correlation in the vertical direction, perhaps unwittingly the correlation between these 2 points will be assigned a low value because they're not on the same horizontal plane. This is something that is very hard to avoid when building a three-dimensional covariance matrix. Hence, normally I don't work with don't build three-dimensional covariance matrices. There may be exceptions if I've got pilot points arranged on a regular grid, but normally the difficulties of handling pronounced vertical anisotropy make this too prone to getting correlations wrong when building a 3D covariance matrix. And that brings us to the end of this video. Thanks for watching.